Okay. So so let's recall from last time that we had this formula, index of d plus is equal to supertrace of exponential of minus t squared, which is the same thing by definition as trace of exponential of minus t plus star d minus trace of exponential of minus t d plus. And then there is d plus, right, d plus star. This is for any t positive. And this was, of course, Atiyah-Singer formula. So then, using kernel expansions, so it follows that we can just write index of d plus as well. I mean, as just integral of little trace of k t x x the volume of x. I mean dx. Yeah, dx, so to speak, over m. Well, this is not, let's just write it because this is a differential form, really. That's an n form, yeah. And this ktxx is, in general, ktxy. So this, as an object, it lives in Sx, fiber of spinors over x, tensor fiber of the spinors over y, dual space, so that if you hit this with an element in Sy, Sy star absorbs that element, lends an element in Sx, and that's. But for trace, you just because of this trace, you just integrate over x equal to y space, which is the diagonal. It's like computing diagonal matrix. Now, of course, we saw that ktxx is asymptotically of the form, there is an asymptotic expansion, minus n over 2 times u0 of x, there is some function, plus u1 of x t, plus u2 of x t2, and there could be infinite number of terms easily. So this is as t goes to 0. Near 0, you have such an expansion. So if you sub this into that, you see, if you have this function asymptotically given by this function, the integrals are also asymptotically given. That's easy to see. So it follows that index of d plus then is basically, yeah, we're just saying, okay, this is equal this integral, but this integral is asymptotically given by that. So you can just write it as 4 pi t minus n over 2. Now, term by term, integrate. So integrate to 0. Now we have to apply supertrace. I mean, little supertrace to each of those. 0 of x over m plus integral supertrace 1 of x over m times t and supertrace 2 of x times t squared, so on, for any t positive. I mean, near 0. This expression is for t near 0. You see, this expression is true for all t, but this expression is for t near 0. So we just, because this is true for all t, we just apply it for small t. But for small t, we have this expression. So this is as t goes to 0. All right. Now, if you look at right-hand side and left-hand side, this is a constant, it's an integer, right? Constant integer. And the only way a constant can be given asymptotic expansion like that, if you go back to the definition of asymptotic expansion, the only way for this to hold is that all terms vanish, except there is one term where this power here is matched by this power. It gives you a constant term. But all other t dependencies should vanish. Okay? So, constant integer, this implies that the only term that actually, index of d plus, first of all, it's literally equal to, because there is no question, but this is t now vanishes if you pick power n over 2 here. So this is 4 pi t, the power minus n over 2 times one term only, and supertrace of u n over 2 of x, right? And then times t n over 2. Now this t minus n over 2, t n over 2 cancel each other. We just chose the power such that they cancel. So this is equal to then 4 pi minus n over 2 integral supertrace of u n over 2 of x over n. Okay, so, and all other terms vanish. I mean, all other integrals should vanish. I mean, do vanish. Because we believe everything here, when we just, okay, do vanish. Okay, so this index of d plus is equal to that expression. Looks like a huge progress because now we have a candidate for the integrand of the index formula. It looks like we can write down index of d plus as some terms. I mean, this integral of this, I mean, there should be the volume of x, of course. I just put x over there. Yeah, the volume of x, right? It looks like that we have made real progress because now you would say, okay, the only thing that we need to do is to compute this term. So let's go back to the proof of this result when people proved that ktxx is given by such expression. They gave us some recipe also to compute these UNs and then find UN over 2, that function, that's the integral you want, and you have proved the index theorem. So this is like the good news. So this formula is the good news. But the bad news is that no one is unable to compute this term per se. This cannot be computed. So let me emphasize, the bad news is that except for few of these terms in general, where there are recipes, there are formulas, U0, U1, U2, up to U6 or U8, then you hit a wall. You hit a wall in the sense that you really face thousands of terms after that. This number of terms in the expression exponentially grows with the dimension of the manifold. And there is no sort of, except very, very general features, there's no pattern to be. So, I mean, it looks like this is a hopeless, okay, so we have done all this work, but we have come to this point. Now we are hitting a wall because we can only compute it up to U8. But the index theorem is true for n-dimensional manifolds for any n. So what is going on? I mean, for example, in the case of Gauss-Bonnet, I mean, this is not a Dirac operator, it's a generalized Dirac operator. But the index of this generalized Dirac operator, there is a very small kind of nice term here instead of this thing. There is Pfaffian of the curvature, that Euler form, that characteristic class that we defined. And there is a big, big difference between that Pfaffian and this sort of thousands of terms. So this was what was already observed by Atiyah-Singer when they got this formula. They noticed that possibly it can be used. They knew all of this stuff, of course, and they reached this. But this is not the usual trace. This is super trace. And they said that maybe somehow magical. We know that, of course, integrals of those thousands, millions of terms, so to speak, has to vanish and give us only integral of one term. But maybe even before integration, they cancel each other by applying super trace, and only one term or few terms will remain. And that's the index theorem. In fact, if you just get few terms, that's your theorem. So this was called fantastic cancellations, or magical cancellations, or miraculous cancellations. So let me write it down. So this was, so I'm going to erase this part. So they had a dream then. So Atiyah-Singer was, this is what is called fantastic or miraculous. I don't know what was the exact wording. I think all of these things is just, it means more or less the same things, just miraculous cancellations. Fantastic or miraculous cancellation may happen. And after applying super trace. Not, and before integration even. I mean, this is important. And before integration. Because you see, if cancellations happens after integration, still there may be a chance, but it means that we don't really understand what terms to identify as the right term. It's like there are a lot of divergence terms, and but which one we have to keep, which one will deliver the index theorem is not. But if before integration, but after super trace, there is cancellations, you have a chance that you really have hit the integrand that's needed for the index theorem. And that's exactly what happened. So sometimes miracles happen. And the miracle indeed happened. Happened to be true. Now, why this miracle happens, nobody knows really. I mean, it's amazing. If you go on like for 500-dimensional manifold, there are millions of terms, and all these things cancel. Only few terms, 1, 2 terms remain, and that's exactly the expression of the index theorem. And this is one of the things about super trace and then some nature of this problem. So we're going now to get to the root of this and then follow this path. So as I said, there were several verifications of this miraculous cancellations, but the best proof eventually, I believe, was given by Ezra Getzler. So today we are going to start along his lines. Okay. But before doing that, but maybe before doing that, let me just draw one consequence of this expression that we found. Okay, I mean, so this will come later on, but maybe just attention now. So a corollary, the formula that index of B plus is equal to 4 pi to the power minus n over 2 integral super trace of mu n of x the volume x over m. The corollary is this. Let until m be a finite covering of course, closed, oriented Riemannian spin manifold M. And let Stilla, E tilde, be liftings of the Dirac operator, spin bundle and Dirac operator from M to M tilde, be liftings of S spinor bundle and D a Dirac operator to M tilde. So you see, what is the situation locally? Locally, you have this M. I mean, there is some, but then over M, there are these copies of a small neighborhood on M, right? So it's like a pancake picture, right? So we have So there is this covering map, and locally these things, the M and M tilde really look like the same. So what we do, we just use this local diffeomorphism between this and that to lift Riemannian metric, to lift spin bundle, to lift the Dirac operator to M tilde. This is called lifting under this covering, right? Okay, so now the question then is, what is the relation between index of D tilde and index of D? Okay, so I would say here finite k-fold covering. Okay, covering of this. Then the claim is that index of D tilde is equal to k times then index of D tilde is equal to k times index of D. Okay. It's just this result that we need in order to prove. We don't need anything deeper than that. And this result is even true for generalized Dirac operators, not just for the Dirac operator. For generalized Dirac operators, it's also true. So this is fine. And so this is called multiplicativity of the index. If you have your manifold and you cover it k times, it's like k copies of the manifold. But I mean, this is not a trivial bundle over n, right? It's non-trivial. But nevertheless, index is still k times index. I mean, proof of this is not difficult now using star. This is star. We can just argue that locally, this expression on the covering space and expression on the base are the same. Because Riemannian metric, we are assuming, are the same, everything. So if you have the heat kernel here, you can certainly make sure, you can certainly know that the heat kernel, is the same. By a star, index of the D tilde plus index of D tilde is 0. Index of D tilde plus is equal to 4 pi minus n over 2 integral m tilde supertrace of un tilde, I just write it like that, x, the volume of x. And to compute this integral upstairs, because it's integration, it doesn't matter. You can chop your manifold into k pieces, and on those boundaries, which have just that two pieces may intersect, that doesn't matter because integration is insensitive to subsets of measure 0. So basically, you can just say that this integral is really k times integral downstairs. That's why.
Sorry, do we mean un or un over 2?
Big part. Oh, un over 2. Yeah. Very good. Thanks. Yeah, exactly. Integral. This is k times. You reduce it to integral down there, and this is locally the same as down here. So supertrace, of course, is the same, but this happens in the same bundle locally. N over 2 of x. I mean, this is. And so this is really, if you have local expressions, then this is the same. Okay, so I mean, this is a kind of example of this you have seen really before, like Euler characteristic. is multiplicative. I mean, chi of n, we argued that this is equal to index of d plus d star, which can be really realized as some of these, as some d plus. Now, the spinor bundle in this case, the generalized spinor bundle is going from even forms to odd forms, and we saw that using Hodge theory or Hodge theorem, we saw that the index of this operator is really Euler characteristic. Okay, so of course, for this, we know that Euler characteristic of k-fold covering is k times Euler characteristic of the base. But now we see something much more general. So this is a good, I mean, a small dividend really of this result. I mean, seeing this in this generality without this formula, I don't think it's very easy. So that's what the what I wanted. What time is it? What I wanted to mention first. Now, okay, very good. Now we want to prepare for the proof. Any questions, by the way? Okay, now there are, after these ideas of heat kernel and asymptotic expansion and this thing, there are three major ideas, as I said before, in the proof. So I will develop those ideas and then we'll start the proof properly. So if needed, one is Berezin integration formula, or I would say traced formula. And second is we need a little bit about harmonic oscillators. I mean, we need the heat kernel of quantum harmonic oscillator. And we also need Weissenburg formula, but Weissenburg already did, right? Yeah. Okay, I have done this already. But we'll discuss it again. I mean, this squared, it was like nabla squared, nabla plus r. So there is this, I mean, this is more or less, we did it. I mean, so now this is the question. Okay, so let's just start with one. Okay, so now what is this Berezin's trace formula? It's a pure, again, pure linear algebra or superlinear algebra relation or identity that's amazingly crucial for the proof. So let n equal to 2m as usual, even number. And let us consider this complexified Clifford algebra, I mean CL of Rn. So this is this complexified.
we have seen that, of course, this is isomorphic to endomorphisms of a yeah, so this is just, you know, it's a matrix algebra, so isomorphic to endomorphisms of S, some space of spinors, but I mean, choosing this S inside Cn, it's there's no canonical choice of S unless you fix a complex structure on Cn, because you complexify Rn, you get Cn, there are different choices. This is S tensor S star, okay? Okay, now, a basis here, a linear, we know there is a linear basis here. For Cliff. Well, you can just pick an orthonormal basis, for example, E1, En. If you want maybe oriented even, that's fine. Oriented orthonormal basis for Rn. Then any element here this C, we can write it as some C, I mean, we have to fix some notation, C, E, I don't know what notation I used. So the notation is C, E, E tilde. Yeah, so C, E, E tilde. You see, E is a subset of 1, 2, n for any subset here. And I used to write something like E I1 times E I2 E Ik. This is E tilde, product of these things, where if E is equal to I1 I2, Ik. But that's a bit cumbersome sometimes, so we just use this as more kind of more slick notation, right? So, but it's the same thing. There are 2 to the n elements in the basis, and these are complex numbers, right? CE belongs to C, complex numbers, and these are elements in the Clifford algebra. And certainly, any element here can be written uniquely in this way. Okay. Now, so what is supertrace now? So this has to do with this picture. Supertrace. Now this supertrace goes from CL Rn to C, right? So what is this supertrace and where it comes from? Notice that we can further decompose S into 2 pieces, right? S, we can write it as S plus, X sum S minus. This is a super vector space. And how did we decompose this S? This was done using a particular element, right? So we just used this element, which was omega, we called it. This was I to the power n over 2 E1 times E2 times En. Remember, there was also an exercise about this thing. I believe it was I to the power n over 2. Yeah, right. So this element, this we can call nu. So this is equal to I to the power n over 2 nu. So what happens is that omega squared is equal to 1. And we use this to decompose S into two pieces. So this is basically the space of, this element belongs to Clifford algebra, right? CLRN. So we look, so it's acting on this vector space. Omega squared is 1. We just took its eigenspace 1 and eigenspace minus 1, or eigenvalue minus 1 of it, right? And this is this S plus and S minus. So we have this decomposition. Okay? Because remember from Monday, because we have this decomposition, we obviously have super trace, as usual, as we discussed last time. So now, this is interesting. Clifford algebra, if you look at it like this, you might wonder, what is going on? I mean, I don't see any trace here. These are just some algebra elements. But if we use this identification, we can think of it as matrices, large sizes. And because we have some super vector space structure on S, we can utilize it and define this super trace. Now, there is a formula for super trace which is very easy, so let me write it down now. So if your operator T was something like A, B, C, D, I said that super trace of T was equal to trace of A minus trace of D. Right? Now, consider this element. So you see, in this decomposition, this element omega is like, it's acting by identity on S plus and is acting by minus identity on S minus. So omega is really this element. If you think about it, in this decomposition. So, I mean, the two things together shows that then super trace of T is nothing but the standard trace of omega T. You see, if you multiply this by this, the effect is changing D to minus T, and you take the usual trace, and you have got super trace. So physicists write Ft for some reason. F is for fermions, and but doesn't matter. Okay, so super trace of T is really ordinary trace of omega times T. This is important. Okay, so we need this background. That's it. Now I can state the theorem, which is the lemma. This is Berezin's lemma. So,
can I ask something really quick?
mm-hmm.
So the original grading on the Clifford algebra coincides with the grading from omega, or because the Clifford algebra is already a super algebra, right? So we're taking the super trace with respect to which grading? Or are they the same?
They're the same, actually.
Oh, okay.
They're the same. Because that omega, with respect to elements of the basis, when you multiply, it commutes with elements of which have even number of degrees, and anti-commutes with elements that have odd number of degrees. So it's the same thing. Yeah.
Right. Okay. Yeah.
Yeah, that's a good point. Yeah. There are yes. Okay. So yeah, that's what it is. Right now, lemma is that yes. Okay. So let me write this Berezin's lemma. Now let's see be equal to some CE tilde over E as the composite, presentation we had, be an element of cliff. Then super trace of then its super trace considered as an element of end of S that we discussed is equal to so let me write it in the following form: super trace of general element of this form is just equal to minus 2i to the power n over 2 C1 2. You see, in other words, we just take the contribution to the expansion of C from the top part, which is C1 2n. This corresponds to E equal to full set 1 to the full subset, which is the same thing as E as set 1 to n. And that's it. So, if you think about it, this is really remarkable because, under this isomorphism here between Clifford algebras and N, a lot of things can happen. Nevertheless, we can always get the value of supertrace by looking at the top part. This is really remarkable. So, have you seen a similar formula before, where to compute a trace or an integral, we looked at the top part of some form or something? Have you seen such a thing before? In this course, maybe?
The integral.
Yes. There was this discussion of Berezin integral on Grassmann algebra, right? We discussed that. So what does this result says is that remember what we had. So here is Clifford algebra, Rn, and here is Grassmann algebra of Rn. Okay, if you like, you can complexify that so that everything is. These two algebras are not isomorphic because this is graded commutative. This is far from being commutative. This is basically a matrix algebra. It's highly non-commutative. But as linear spaces, they are isomorphic. And in fact, if you fix a basis, an orthonormal oriented basis in Rn, you get an isomorphism even. So as algebras, these are isomorphic. As vector spaces, these are isomorphic. Now look, we had this Berezin integration, right, here to C. And here we have this super trace to C also. And what we are saying is that these two things are equal, but now I have to multiply here by this constant factor minus 2i to the power n over 2. So I just multiply minus 2i power n over 2. So this diagram, if you want, you can write it as a diagram. You have isomorphism, this diagram commutes.
i.e. block diagram. Commutes. Now, what was this integration? Remember, integral, Berezin integral, I defined it when we were discussing Pfaffians and fermionic integration and Grassmannian and in the context of, I mean, fermionic Gaussian integrals and so on. Remember, so this was an expression that sum AI EI1 wedge EIK. Here I put I1 IK over all things 2 to the n terms. This was by definition just the top part, right? A1 to n. This was Berezin's integral here. In this case, this is the supertrace, and the two things are the same. So now, again, this is quite remarkable because if this was an isomorphism of algebra, this would be obvious. But this is not an algebra isomorphism. Nevertheless, the diagonal commutes. And so here we are in this non-commutative world. Things are very, very complicated. We come here, makes things much easier for us, but nevertheless, we don't lose sight of trace. And super trace, not trace, super trace. And super trace is the only thing we need to compute in order to prove the index theorem. So this is one of the steps, algebraic underpinnings of the index theorem. So I want you to really appreciate the power of this amazing observation by Berezin. I believe in some, this was also observed by Patodi independently of Berezin in a related context. But Patodi was not aware of physics or superalgebra or fermions and stuff like that. He was just he was really master of tensor analysis, and he saw that he could prove this, and then he proved index theorem using heat equation methods for Laplace operator, which is this Gauss-Bonnet theorem. That was his thesis, I believe. Anyhow, so let's now get to the proof of this Berezin's lemma. So have this picture in mind. This is very important. Let's get to the proof now. Okay. Since I just write it like this, since supertrace of C is equal to trace of, I still have it here, trace of omega C. But omega, we know what element is it. This is I to the power n over 2 nu C. Remember, nu is this element E1, En, right? So suffices to show that if you want to compute this trace, it's enough to show that usual trace of any C of the form C T is equal to 2 to the n over 2
C empty for C is equal to sum CE times E tilde over E. So in other words, what is this CMT? This is the coefficient of 1 in the expansion, because there is a 1 here, which corresponds to empty subset. And you go up to the full subset, which is the whole thing. And the coefficient of the empty things, this is 1. This element is really 1. So this is coefficient of 1. 1 in the expansion. Right? I mean, how do you get, if you prove this, you have to, because we have the coefficient of 1, so when you multiply, it means that we are taking the top part. So this is all we have to prove. You think about it. Okay, how do we prove this though? Okay, so maybe I give it, because I gave an argument for myself, so maybe I give this argument to you too. So since, then we can write, yeah, it's not, it's a little more explanation, because I have it here, trace S of C, well, I just write myself again, this is equal to I to the power n over 2, usual trace of mu C. This is equal to I to the power n over 2, 2 to the power n over 2, C1, 2, and then we have got E1 EN squared. So this is equal to 2 to the power n over 2. And then we have 2 to the power n over 2, I to the power n over 2, sorry. And then we've got minus 1 to the power n over 2, C1, 2. Yeah. So the idea is that to find the constant term of this, I mean, this is not properly written really. You compute the constant term of this. This term is E1, yeah. And the only way you can reach the constant term of this is you pick the top part of C, which is as a coefficient of E1, E2, En, and then C1 to N is that coefficient. So this is not quite correct. I mean, but you have to multiply this by that and then pick this coefficient, not C1 to N, just because you multiply these two things. And this is all because if you assume that this formula is correct, which is the main thing to prove now. So let's call it a star. So this is the argument why proving a star is enough to prove the whole thing. So now we go back to proving the star. Yeah. Okay, maybe I'll just finish the proof because it's kind of, it's a one line now. Well, it's not one line. Yeah, so a little more than one line. Okay. We need to prove that. Trace of basically E tilde. I mean, because we want to compute trace of such a thing. So we have to show that trace of such a thing is equal to 0 for all contributions from E except E equal to empty. Those things we have to show they are 0. So in other words, we have to prove that this is equal to 2 to the power n over 2 if E is equal to empty and 0 otherwise. Okay, now, if, I mean, this case is obvious, right? The reason is that if E is empty, then this E tilde is equal to 1, right, in this case. And then this operator C, so 1 belongs to endomorphisms of S. It acts as identity on this vector space, identity transformation on this vector space of dimension n over 2. I mean 2 to the power n over 2. So in that case, we know that trace is equal to rank of 1, which is 2 to the n over 2. I mean, so we are in this first case. So since trace of 1 of S is equal to dimension of S, 2 to the power n over 2 indeed, you're done in this case. So the first case is easy. Now, the second case is very mysterious, right? Because we have these Clifford algebra elements. They act on S in some ways. And I mean, who says that the trace should be 0? I mean, so there are like zillions of cases in this case. I mean, all kinds of different things can happen. This is another thing that to think about, to marvel at. I mean, this is why this is the case. Now, one thing is clear. If E is not empty, so action of, first of all, action of Cliff on itself on Cliff Rm. Any algebra is a module over itself, right? So this acts on itself. Now, if E is different from empty, then by action, of course, I mean the left action, right? Left regular action. If you think about it, because this E is not empty, E tilde is different from 1. So it means that this E tilde element moves all elements of the basis to some another element of the basis, not to itself. Because when you multiply basis elements by this fixed E tilde, you just multiply those Clifford algebra elements. And they are not going to be the same. Just think about it, because that element is invertible. Okay? If they are going to be the same, you can cancel and you can show that actually E has to be 1, E tilde has to be 1, and you know that E tilde is equal to 1 if and only if E is empty, but we are assuming E is not empty. So that's the argument. Okay, so let me write it. And E tilde moves any basis element. Just write it like EI1 dot EIP of Cliff Rn to a different element. Definitely a different element. So you have this vector space. You have a basis for your vector space. The vector space is cliff itself. The basis for the cliff are these elements ei1 dot eip for all subsets. Basically all etillas, if you want. And you have this operator multiplication by etilla, which moves all the elements to something else. So of course the trace is 0, right? Because on the diagonal, as a result, nothing remains. On the diagonal is 0. So this implies that, so let me write it here. So it follows that trace, the usual trace of etilla is equal to 0, since the matrix of etilla in the standard basis for cliff has no elements on the diagonal. In the basis that I just discussed has no diagonal element. Okay. So this is a, remember so far, I mean, this is a tricky argument. Okay. But we are not done, right? We showed that trace of etilla as an element, as an operator acting on cliff to itself is equal to 0. But we are not interested in that. We are interested in kind of a square root of that situation. We are interested in acting on end of S, right? So let me write it now like this, but so trace of, so etilla as an element from cliff Rn to cliff as trace 0. But we are interested in trace of etilla as an element from S to S. We want to say that trace of etilla is equal to 0. Why? Well, here is where we need some representation theory of Clifford algebras. The thing is, this representation, we have isomorphisms of modules. Cliff module, isomorphisms. Cliff of Rn is isomorphic to S tensor S star. But be careful what we are saying here. This is, we know, this is isomorphism of algebras, but we are not using that. This is a Cliff Rn module. And this is also left regular module. This is also a Cliff Rn module. Now, this is star here. It's like in this action, in this isomorphism, it's like just like, the action of cliff here, this is like dangling there. It doesn't act by identity here. You see, because if this is a Cliff Rn module, you tensor it with any vector space, it still is Cliff Rn module. Just act on here. On this one, acts by identity. This is very basic page 1 of module theory, right? If you have an A module, you tensor it with any vector space or ring or abelian group, whatever category you're working on. This is still a module over your original algebra because this is. And now we are saying that these two modules are isomorphic. And the reason for this is that Clifford algebra, in this case, has a unique irreducible representations, and all other representations
Cliff Rn are basically of this form. This is just a statement from representation theory of Clifford algebra. I mean, we have proved some elements of it, like the existence of this irreducible representation of that dimension, but you can move on and then prove more general. So this is basically representation theory of Clifford algebras. Implies this. Okay, so that's pretty good. Now, to compute trace, you can compute it either here or over there, because these modules are isomorphic. Okay, now, but trace of E tilde as a map from S tensor S star to S tensor S star, what is that? That's equal to trace of E tilde as a map from S to S times, here is just identity, and trace of identity is just 2 to the n times 2 to the n. But on the other hand, I know that this is equal to trace of E tilde as a map from Cliff Rn to Cliff Rn. But we just argued here that this is 0. So this is equal to 0. So this is 0, so this is not 0, so this better is 0. And that's what we wanted to prove. So this is a highly non-trivial fact. This is really hidden inside this super trace and this representation theory of Clifford algebra. It's purely algebraic fact. We can say it's linear algebra, but it's very deep fact, a very deep fact. And this is what we need in order to, I mean, one of many things we need in order to prove index theorem. Okay, so I just take a break and we come back in 10-15 minutes, maybe 15 minutes at 2:25, I'd say, and we continue with some, then we do some analysis of quantum harmonic oscillators to get it out of the way, and then we'll look at them. Okay? Okay, so now let us change gears and do more analysis. Okay, so we need, as I said, some stuff about quantum harmonic oscillator. So what we need is this operator H. I mean, you really don't need physics to understand this stuff. I mean, physics is in the background of this, but I mean, we just consider this operator, which is minus d2 dx squared plus 1/2 a x squared, I believe. No, no, you just put x squared, a squared. So that's an unusual choice of constants, but that's okay. So a is positive. So what is this? This is an operator, right? I mean, so for any phi, say belonging to now C infinity of R,
I mean, without caring about the, the growth condition at infinity, just take smooth function. Then h of phi is the following function. H of phi is a function at x is equal to minus phi double prime plus a2x2. And then times phi of x. So this part is called the multiplication operator. This is the multiplication operator. And this term is usually called potential. And this term is, of course, you can see that this is just Laplacian on the line, right? This is Laplacian. I mean, this is a, yeah, this is Laplacian. Okay, so this, you can say this is like a Laplacian plus this multiplication operator. Now you can guess what's going to happen for our Dirac operator, because we are interested in d squared, e to the minus t d squared, and we are interested in its trace, super trace. So first of all, d squared. D squared, we will show that in some good, well, first of all, we know that d squared by Weizenburg formula is equal to essentially nabla star. Nabla, and then there is some term r. And you see what's going to happen, that in some abstract sense, this is going to be like this. This is the kind of Laplacian in some coordinates, it's like that, multidimensional version of this. And this term corresponds to harmonic oscillator, the potential term. So, okay, this is the first idea. I mean, a very, very approximate idea why we are interested in this analysis of this operator. Now, the next step is we want to know the kernel of this, right? An expansion of the kernel of this guy. Well, then we want to know kernel of this operator, e to the minus th, its kernel. And kernel of e to the minus th for h, a harmonic quantum harmonic oscillator, turned out that it was kind of found by mathematicians long before quantum mechanics, actually. There's a formula due to a guy called Mailer that gives you this kernel, actually. Gives you kh of txy. And that's what we need, because we want to analyze the kernel, so we better analyze such kernels. So, okay, so now let's go back. So this is the motivation why we are interested in such operators. Now let's go back to analysis over here. Okay, so basically what we want to know know the eigenvalues and eigenfunctions of this operator. So basically we want to know eigenvalues, eigenfunctions, and heat kernel of H. So what are they? We want to construct them. So in other words, basically we want to solve equations like this: H phi equal to lambda phi, Now, this phi has to be in, has to be in L2 of R. There should be some decay condition at infinity. I mean, if you don't impose a condition like this equation would have any solution for any lambda, because this is a second order differential equation. For any lambda, it's still second order, you get two solutions. That's it. So that's not what we want to do. We want to find a kind of solutions that have some decay at infinity. In other words, they're all L2. It turns out that all solutions will be actually much better than L2, so rapid decay at infinity. And they are much better than just being C2, they are C infinity, it turns out. So we want to find them. So, and then what are lambdas, what are phi's, and then what is K of Txy? That's our goal, really, to get that K of Txy. Okay, so now there are different ways to achieve this. Several methods to achieve this. A kind of quick method, which is essentially due to Dirac, is the following. So I'll tell you the whole story now. So let's consider this operator. I mean, this is called annihilation operator. A. So this annihilation operator A is basically x plus b dx, is some form of x plus b dx. So A is, ax plus b dx. Remember, A is positive. I mean, this is first order differential operator, right? This is first order. And we define also a star. And there is this creation operator. A star is equal to ax minus b dx. Now, first of all, there is this easy exercise. Check that at least A star is formally adjoint to A. A star is a formal adjoint. I mean, the reason for A star, I mean, formal adjoint of A, in the following sense, inner product of A phi and psi is equal to phi, and A star of psi, i.e., I would say i.e., for any phi and psi belonging to, I mean, C infinity, C of R, but you don't have to be so restrictive. You can just assume C2 functions that have some decay at infinity. They go to zero at infinity and they are, this holds. I mean, it doesn't matter. So, but this is a nice, so what is this inner product, by the way? Of course, inner product of phi psi is equal to integral phi psi bar over R. This is the inner product. Right? L2 inner product that turns this into a Hilbert space. Okay, so we have that. Now, why this is called annihilation? Why this guy is called creation? Well, this is the way actually the world works. Particles are created and annihilated by applying this operator. So the whole creation annihilation in the world is based on these operators and their generalizations. So I don't want to get into that, but these are very, very fundamental. You see that they are given a very serious terminology: annihilation operator, creation operator. So you're dealing with big time items. Okay, that's one thing.
Now, there is some algebra that's important, so you can check that AA star is equal to H plus little a, and A star A equal to H minus A. These are elementary to check. Commutator of AA star equal to 2A commutator of H and A equal to minus 2A times A, and commutator of H and A star is equal to 2A A star. I mean, all these things are purely algebraic. You can check that. So that's yeah, that's okay. Now we have to find these phi's. Now, I mean, we really have to find eigenvalues and eigenfunctions. And I won't give Dirac's argument or physicist's argument because there is some flaw in that argument, basically. But the way, so we are using really half of Dirac's technique. We introduced creation and annihilation operators, but now we are kind of, we're going to start from the end of this story. Okay, so let me just tell you what we want to do. Definition. The ground state of H yeah, maybe this and that, just these two I give as exercises so that you can try your hand with this sort of algebra. The ground state of H is psi 0 belonging to L2 of R such that A of psi 0 is equal to 0. It's annihilated by A completely, and the norm of psi 0 is equal to 1. I mean, it's very easy to find psi 0. You see, what was this creation operator? A of psi 0 is equal to A was what? ddx plus AX, was it? Yeah, AX plus ddx. So you put times psi 0 equal to 0. So this is a simple, very easy differential equation. You can easily get that there is a unique solution. I mean, it's a first order calculus 1000 differential equation, really. And we can say find C0 of x equal to C exponential of minus A over 2 x squared, Gaussian. For a suitable constant, C is fixed by demanding that norm of psi 0 equal to 1. So this is the Gaussian. So the first, so the ground state is the Gaussian. The variance of the Gaussian, the mean is 0, and its variance is related to this A, to the constant of the problem. So this is of course, I didn't say it, but the interpretation of A is that this is related to Hooke's constant for the spring, for classical harmonic oscillator, right? So this is related. So this is this.
Okay, that's easy. Now we are going to create lots of functions by applying creation operators to this psi 0. So this is the ground state. Okay, so well, this is a function. So far we haven't like this is just a definition, and we were able to show that the problem that we set for ourselves has a unique solution in these conditions, and that's easy. So now for k bigger equal to 1, let us define psi k of x to be a star to the power k. Okay, so maybe I'll just put the coefficients here. 1 over 2 ka square root, yes, a star psi k minus 1. Okay, so you apply creation operator many times, k times, to psi 0 in order to get to psi k. So you create and create and create. So you get series of functions. So now, so far we have created this series of functions, psi k of x, k from 0 to infinity. And this series, it's pretty nice actually. You can show that these are all eigenfunctions of h. So let me just briefly write it like this, using the commutation relations that I wrote down here, I just erased. One shows that. I mean, that's pretty easy. Actually, h of psi k is equal to 2k plus 1, I believe, times a times psi k. Yes, for k equal to 0, 1, 2. Okay, so a norm of psi k is equal to 1. This is psi 0. Okay, so that's pretty good because with this sort of device, at least now we have found some eigenfunctions and some eigenvalues, corresponding eigenvalues, right? But now the question is, who says there are no other eigenvalues and eigenfunctions? So this is a question that usually physicists don't discuss because they say, so the faulty argument on their part is that they say this is a self-adjoint operator. It is self-adjoint in many different ways, but this is self-adjoint. And they say that, well, they just rely on matrix intuition and it's self-adjoint. You look at its eigenvalues, it gives you an orthonormal basis. So this is an orthonormal basis for this space. But in infinite dimensional analysis, this is totally not enough. I mean, so question, are there any other eigenvalues or eigenfunctions? Of H? And the answer is no. And one way, easy way now to prove this is to show that actually the psi k's that we obtain form an orthonormal basis for L2 of R. That's, if you prove that, then that's it. There are no others. So suffices
show that this psi k from 0 to infinity is an orthonormal basis for L2 of R. Now, if you think about it, this is quite remarkable that you have found a kind of discrete set, psi 0, psi 1, psi 2, that gives you an orthonormal basis for L2 of R. I mean, starting with this, next one is like this, and then the other one is just goes like this, and so on. So I highly recommend you open Wikipedia or other or favorite book on quantum mechanics or just any document online and check the shapes of these psi k's. They are beautiful, and it gives you a basis, orthonormal basis for L2 of R. Now, R is not compact, and in non-compact spaces, any orthonormal basis like this is quite hard to achieve. I mean, especially if you want to have explicit formulas. Anyhow, so suffices to show that this. Now, one thing that from this sort of course, I mean, psi k, psi L inner product, this is easy from the definitions and commutations relations. This, I tell you, this is easy. That's not a problem. Another thing is that this psi k, actually we know how it is. You see, for example, psi 1 was a star, psi 0 some constant, psi 2 was another constant, well, I mean, this is C1, another constant, C2, a star squared, psi 0, psi 3 is another constant, a star cube, psi 0, yes, so on. But what was a star? A star was dx minus ax, right? So, but what was psi 0? Psi 0 was some constant itself times exponential of minus, so let me write it now. This is equal to C1 ddx minus ax exponential of minus a over 2. This is this Gaussian. Right? So when you apply this differential operator to this, to Gaussian, you're going to get a function which is like a polynomial times Gaussian. Right? So it's a polynomial times Gaussian. So in other words, this psi k of x, at least it's a structure, we know what it is. This is a polynomial, like I call it pkx, times exponential of minus a over 2x2. This is clear. Psi 0 degree of this polynomial is equal to k. We know that because you see, this comes down, gives you degree 1, and then there's degree of pk equal to k. These are called Hermite polynomials. Famous polynomials in the theory of orthogonal polynomials. This is called Hermite polynomial. So now time is up. So now what we want to show is that basically the set of all such polynomials times exponential of minus a over 2x squared is a dense subset of L2 of R. In order to show that, because these are orthonormality relations, to show that forms a basis, you have to show that the linear span of these things is basically dense. So that's the last step for now. Let me just write it. So now claim is that the set of all px exponential of minus A over 2 x squared, where px belonging to C of x, a polynomial. I mean, I would say linear span of these things. Linear span of these things inside L2 of R. Remember, all these guys are in L2 of R because of this damping factor that's there, right? So linear span of such things is dense. So this linear span is dense. Now, this is quite a tricky argument. Let me just briefly give you the argument. This is quite tricky. Proof. All right. I mean, the way to do this is to show that if a function is orthogonal to all these things, then that function is 0. Okay. So we show G is orthogonal. So let's call this subspace W. W, we show if G is orthogonal to W. I mean, this whole linear span, we call it W. Then G equals to 0. This shows that the closure of W is, because I mean, if G is orthogonal to W, then G is orthogonal to W closure. And if you have a closed subspace such that its orthogonal complement just consists of 0, then that subspace is 0. Now, how we are going to prove this? The proof is based on Fourier analysis. Okay, so let me just quickly say the trick now, give you the trick. So let Fj of x be equal to x to the power j. We just pick some elements here, x to the power j, e to the minus x squared over 2. I mean, assuming a is equal to 1 now. I mean, it doesn't help to carry this a. I mean, the argument works for all a, so we just take a equal to 1. So j equal to 0, 1. Now, if you look at norm of these things, it's easy to see that norm of Fj squared is equal to gamma j plus 1/2. I mean, to compute this norm, you have to compute some Gaussian squared times some polynomial, I mean some monomial in this case. And these integrals are very easy to compute in this case because you get even powers here. That's basically trivial to compute. So this is less than or equal to j factorial. So then you can form a series. This series e to the I lambda x minus 1/2 x squared equal, which is equal to sum j from 0 up to infinity I lambda to the power j over j factorial. We're just expanding it times fj of x. You see, this is just x to the power j. And times e to the 1, so this is this factor x to the power j times e to the power minus x2 over 2, which is fj. So the right hand side
because of this star is L2 convergent. If you take L2 norms of this right-hand side, this is convergent because of this star. For any lambda. Yeah. No, I'm a bit now worried because I've got gamma j plus 1/2. This is less than j factorial. I have j factorial here. That's not good. No. I mean, morally, this is j minus half factorial. Gamma of j plus gamma of s is morally s minus 1 factorial. Yeah, there is an issue here, really. What are we talking? So this is like so, no. Okay. Okay. All right. Yeah, I don't like the argument because this only gives me j factorial. If it is less than j factorial, that's not good. I mean, yeah. I need better estimate here. Okay, so now if, so let me just, so this is something I have to think about. So maybe on Monday I will tell you. So assuming I get this convergence, then it means that this guy, lambda x minus 1/2 x2 actually belongs to W closure. It's in the closure of W because look, this is a sum of elements in W, but we are taking L2 limit. So this is really in, look, is e to the minus x squared times some polynomial, and then you're just taking L2 sum. So this is in W bar, right? Okay, now G perpendicular to W implies that G is perpendicular to W bar, implies that G and inner product of G and this guy is 0, right? Is equal to 0. But what does this mean? Let's look at this. What does this statement mean? I want to finish now because I just need 1 minute, that's it. What does this statement mean?
Well, let us write it. This just means integral gx e to the I lambda x e to the minus half of x squared e to the I lambda x dx over r. I mean, we have to complex conjugate this part, so minus dx is equal to 0. Do you remember what kind of object this is? From your Fourier integral thing? This is nothing but Fourier integral of g of x. Fourier integral of g of x e to the minus 1/2 x squared Fourier integral on lambda. Because what we do when you take Fourier, you take the function, multiply by e to the minus I lambda x dx, integrate. Okay, so what did you discover? We discovered that this function g, whatever it is, if you multiply by e to the minus 1/2 x squared, take its Fourier integral is 0 for all lambda. But then there is this powerful result called Planchar's formula. In particular, it shows that, Fourier integral is just injective. It preserves norms. Norm of g of e to the minus half x squared, L2 norm is equal to L2 norm of its Fourier transform. This is one of those magic formulas in mathematics that L2 norm of the function and L2 norm of the Fourier transform is the same. But we just discovered by that device that this is 0. So this better be 0. So g e to the minus 1/2 x squared is equal to 0. But this Gaussian is never 0, so g is 0. So this is the argument to show that these Hermite polynomials times Gaussians for a orthonormal basis or a complete orthogonal set. And okay, so let me just